Midas NFX Simulation Lecture 3 Linear Buckling. This is a cantilever beam. We have drawn the model in SolidWorks, which is 10 meter long, and the cross-sectional area is 50 millimeter by 50 millimeter. So it is 5 by 5 centimeters cross-sectional area, and the length of the beam is 10 meters long. So this is the beam, and we save as a parasolid model, and we're going to perform a buckling analysis. So now in Midas NFX we open a case, give it the name 003, and import the geometry from SolidWorks parasolid file. So this is the first step of analysis, opening a case and importing geometry. The second step will be the material. First of all, we will load a material, isotropic material, 1020 mild steel, and I'll change the Young's modulus to be 3 times 10 to the 11 and Poisson's ratio of 0.3, so that my calculation will be easier, and the result will be that the buckling load will be 3851 newtons, so I can check the answer with the theoretical value. So we can connect the material properties with the geometry. There's only one object, so we simply choose mild steel 1020. So this is the second step. We load the material and connected the material with the geometry. The third step will be the mesh, and I'll choose the geometry, and I'll define the size of the mesh and perform the meshing. This is the step 3, and I can hide the mesh or show the mesh. I'll let it show for now. For step 4, we're going to define constraints or boundary conditions, and I rotate by pressing the middle mouse button and zoom in so that I can choose the surface. I'll choose the entity as the surface. This will be the fixed, and I'll select totally fixed surface. So this is the first part of the step 4. The second part will be the load. So I choose the concentrated force as a type of the load, and I'll choose surface, this surface, as the surface of the load. And for the direction of the load, I can change to surface, but now I will choose this edge to indicate the direction of a force. And you can see that the direction pointed toward the origin of the fixed end. So I can simply place a 1 Newton force, which will be in compression, right? Because the direction here, x direction, will be in compression direction. You can see from the axis here. So I'll give it 1 Newton. So the type of the load will be concentrated load. The surface of the load will be the end surface here, right? The end surface here. And the direction of the load will be indicated by the edge here, and the x-axis will be pointed to the right. So I give it a 1 Newton force, which will be in compression. So this is the end of step 4. So up to now I have finished with step 1 through step 4, and so I have finished with preprocessors, and the problem is fully defined. And then I'll proceed with analysis. For analysis, I will include a linear buckling analysis type and edit the content so that the eigenvalue, the number of eigenvalues to calculate, will be the default 10. 10 is more than sufficient for me, so I'll leave it as default 10 eigenvalues to calculate. So I'll proceed with calculation, solving. This is step 5. And now for step 6, it is the result. I'll take a look at the result first. And this will be the eigenvalue, 3859. So let's get the theoretical value, 3851. So for the lowest eigenvalue, lowest mode, it is very close, right? The theoretical value, by calculating from solid mechanics or mechanics of materials, the answer will be 3851 Newton. And the CAE result is 3859. So the difference is very, very small. But if we look at the second mode, the theoretical value and the CAE data will be quite different. For example, the theoretical value will be 35795, and the CAE analysis will be 34734. So it is about 1% difference. So the higher modes you calculate, the higher the deviation from theoretical value. But beware that actually it is the 3D model calculation will be more precise, the result, because in solid mechanics or in mechanics of materials, we calculate the beam by simplifying the 3D model into a line, a neutral axis. So this is a 1D, one-dimensional simplification result. So only the lowest mode is very close to the 3D result. So we will trust the CAE result more than the theoretical result, because it is a simplified 1D simplified analysis. Okay, this is the third lecture for Midas NFX. It is a linear buckling problem.